The universe is expanding, but here's the twist. It's not just growing, it's speeding up. Every second, galaxies are racing away from us faster than ever before, as if some invisible hand is stretching the fabric of existence at an ever-increasing pace. Picture, if you will, a balloon inflating not steadily, but with a force that grows stronger over time. What could possibly be driving this cosmic acceleration? And what does it mean for the future of everything we know? This isn't just a question for astrophysicists, it's a mystery that challenges the very foundations of physics, forcing us to rethink what we thought we understood about the universe. From dark energy's enigmatic push to the possibility of entirely new dimensions, the theories behind this accelerating expansion are as mind-bending as they are groundbreaking. In this video, we'll dive into 20 pioneering ideas that scientists have proposed to explain this cosmic puzzle. Each theory offers a unique lens through which to view the universe, and together, they paint a picture of a cosmos far stranger and more complex than we ever imagined. So, are you ready to explore the forces shaping the fate of everything? Let's begin. In 1998, a discovery shook the world of astrophysics to its core, and it all began with the faint light of exploding stars billions of light-years away. Astronomers Saul Perlmutter, Brian Schmidt, and Adam Rees were studying distant supernovae, specifically a type known as Type Ia, which act like cosmic lighthouses. These stellar explosions have a predictable brightness, allowing scientists to measure their distance and, by extension, how fast the universe is expanding. What they found was nothing short of revolutionary. Instead of the universe's expansion slowing down, as everyone had assumed due to gravity's pull, it was speeding up. Imagine throwing a ball into the air, expecting it to fall back, only to watch it shoot faster into the sky. That's the kind of cosmic surprise they uncovered. This groundbreaking discovery earned them the Nobel Prize in Physics in 2011, but its implications went far beyond accolades. It completely upended our understanding of the cosmos. For decades, scientists believed that gravity, the force that binds planets, stars, and galaxies together, would eventually reign in the universe's expansion. But this observation suggested something else was at work, a mysterious force pushing the universe apart at an ever-increasing rate. Enter dark energy, a term coined to describe this unknown phenomenon. Dark energy has since become one of the biggest puzzles in modern physics. It's thought to make up about 68% of the universe, yet we know almost nothing about what it actually is. Is it a property of space itself, a new kind of energy field, or something entirely beyond our current understanding? Whatever it is, its existence has forced us to rethink the very fabric of reality. This discovery didn't just change the way we see the universe, it opened the door to a flood of theories trying to explain why the cosmos is behaving this way. And that brings us to our first theory, which dives headfirst into the enigma of dark energy and what it might mean for the ultimate fate of everything we know. One of the earliest and most enduring explanations for dark energy traces its roots back to none other than Albert Einstein. In the early 20th century, Einstein introduced a term into his equations of general relativity called the cosmological constant. His goal was to describe a static universe, one that wasn't expanding or contracting but perfectly balanced. At the time, this idea made sense. The prevailing belief was that the universe was unchanging. But when Edwin Hubble discovered that the universe was, in fact, expanding, Einstein reportedly called the cosmological constant his greatest blunder and dropped it from his equations. Fast forward to the late 1990s, and Einstein's so-called blunder suddenly didn't seem so misguided after all. The discovery of the universe's accelerating expansion brought the cosmological constant back into the spotlight. Scientists realized that this term, originally introduced to keep the universe static, could actually explain why the cosmos is stretching faster and faster. In this context, the cosmological constant represents a form of energy inherent to space itself, a kind of background hum that fills the universe and drives its expansion. Think of it like this: if space were a vast, silent room, dark energy would be the faint, almost imperceptible hum of a machine running in the background. You might not notice it at first, but it's always there, subtly influencing everything around it. In the case of the universe, this hum isn't just a sound, it's a force, gently but relentlessly pushing galaxies apart. Yet, as elegant as this theory is, it's not without its challenges. One of the biggest mysteries is what scientists call the cosmological constant problem. Simply put, the observed value of dark energy is unimaginably tiny, so small that it defies our current understanding of physics. If we calculate the expected energy of empty space using quantum mechanics, we end up with a number that's about 120 orders of magnitude larger than what we actually observe. It's like expecting a thunderous roar but hearing only the faintest whisper. This discrepancy has left physicists scratching their heads, wondering why dark energy's influence is so subtle. Could it be that we're missing a crucial piece of the puzzle? Or is there something fundamentally flawed in how we're approaching the problem? While the cosmological constant offers a compelling explanation for dark energy, its unresolved challenges have inspired scientists to explore alternative theories. Some suggest that dark energy isn't a constant at all, but a dynamic force that changes over time. Others propose entirely new frameworks, reimagining the very laws of physics to account for the universe's strange behavior. These ideas take us even deeper into the unknown, challenging us to think beyond the familiar and venture into uncharted territory. So, what if dark energy isn't a constant hum, but something more complex? A force that ebbs and flows, or even one that connects to dimensions we can't yet perceive. That brings us to our next theory, which dares to imagine a universe where dark energy is anything but constant. What if dark energy isn't a constant hum filling the universe, but something far more dynamic, something that ebbs and flows like the tides or shifts with the seasons? This is the intriguing idea behind Quintessence, a theory that reimagines dark energy as a field that changes over time and space. Unlike the cosmological constant, which suggests dark energy is unchanging, Quintessence proposes that its strength can vary, offering a more flexible explanation for the universe's accelerating expansion. Imagine a river flowing through a vast landscape. Sometimes it's a gentle stream, barely noticeable, while at other times it swells into a powerful current, shaping everything around it. Quintessence works in a similar way. It's not a fixed force, but one that can evolve, potentially growing stronger or weaker depending on the conditions of the cosmos. This variability makes it a compelling alternative to the cosmological constant, as it could account for observations that a static dark energy might struggle to explain. One of the most exciting aspects of Quintessence is its potential to interact with other forces in the universe. Unlike the cosmological constant, which operates independently, Quintessence could have connections to gravity, electromagnetism, or even the fabric of space-time itself. This opens up new possibilities for solving some of the cosmological constant's biggest puzzles, such as why dark energy's observed strength is so vastly different from what quantum mechanics predicts. But Quintessence isn't without its own mysteries. If dark energy is indeed dynamic, what causes it to change? Could there be some underlying mechanism, some cosmic rhythm that dictates its behavior? And how does this variability affect the universe's long-term fate? While the cosmological constant suggests a future where the universe expands forever, Quintessence leaves room for more dramatic possibilities, perhaps even a scenario where dark energy eventually reverses its effects, causing the universe to collapse in on itself. This theory also raises profound questions about the nature of reality. If dark energy can change, what else about the universe might be more fluid than we once thought? Could other fundamental forces or properties of space-time also be in flux? Quintessence invites us to think of the cosmos not as a static stage, but as a living, breathing entity, constantly reshaping itself in ways we're only beginning to understand. As we explore these ideas, it's clear that Quintessence offers a fascinating perspective on one of the universe's greatest mysteries, but it's not the only way to approach the problem of cosmic acceleration. What if the answer lies not in dark energy at all, but in the very laws of gravity themselves? That brings us to our next theory, which challenges us to rethink one of the most fundamental forces in the universe. What if the problem isn't with dark energy, but with gravity itself? That's the bold question at the heart of modified Newtonian dynamics, or MOND. This theory dares to challenge one of the most fundamental forces in the universe, suggesting that our understanding of gravity might be incomplete, especially when it comes to the vast cosmic scales of galaxies and beyond. Instead of invoking dark energy to explain the universe's accelerating expansion, MOND proposes that gravity behaves differently on these grand scales, rewriting the rules of the game entirely. Imagine you've been playing a board game your whole life, only to discover that the rulebook you've been using is missing a few crucial pages. That's essentially what MOND suggests about gravity. For centuries, Newton's laws and Einstein's theory of general relativity have been our guides, describing how gravity works with incredible precision, on Earth, in our solar system, and even in many galactic contexts. But when we look at the motion of stars in distant galaxies or the behavior of galaxy clusters, something seems off. The observed movements don't always match the predictions of these well-established theories. MOND steps in to fill this gap by proposing that gravity weakens less quickly over large distances than Newton or Einstein predicted. In other words, it doesn't follow the inverse square law as strictly as we once thought. This subtle tweak could explain why galaxies rotate faster than expected, and why the universe appears to be expanding at an accelerating rate, all without the need for dark energy. It's like discovering a hidden rule in the game that suddenly makes everything click into place. One of MOND's most compelling successes is its ability to explain the rotation curves of galaxies. These curves describe how stars and gas move around a galaxy's center, and under Newtonian gravity, they should slow down the farther they are from the center. But observations show that they don't. They maintain high speeds, hinting at the presence of unseen matter, or, as MOND suggests, a different set of gravitational rules. By modifying gravity, MOND provides an elegant alternative to the dark matter hypothesis, which posits the existence of invisible particles to account for these discrepancies. However, MOND isn't without its challenges. While it excels at explaining galactic-scale phenomena, it struggles to account for larger cosmic structures, such as the distribution of galaxy clusters or the precise details of the cosmic microwave background radiation. These observations align more closely with the predictions of general relativity and the standard model of cosmology, which includes dark energy and dark matter. This has left many scientists skeptical about whether MOND can fully replace our current framework, or if it's simply a piece of a much larger puzzle. Despite these limitations, MOND has sparked important conversations about the nature of gravity and the universe. It reminds us that even the most fundamental laws of physics are open to reinterpretation, especially when faced with observations that defy explanation. Could gravity be more complex than we've imagined, or is MOND pointing us toward a deeper truth about the cosmos? As we continue to explore these questions, another radical idea emerges, one that takes us beyond gravity and dark energy entirely. What if the universe itself is a kind of hologram, a projection of information encoded on a distant surface? This is the holographic principle, a theory that reimagines the very fabric of reality. But to understand how it connects to the accelerating expansion of the universe, we'll need to take a journey into the mind-bending world of quantum physics and higher dimensions. Imagine holding a credit card in your hand. On its surface, there's a small holographic sticker, a flat, two-dimensional image that somehow creates the illusion of depth, making it appear three-dimensional. Now take that idea and scale it up to the size of the universe. What if everything we see, the stars, galaxies, and even the vast expanse of space itself, is nothing more than a projection, a hologram encoded on a distant two-dimensional surface? This is the essence of the holographic principle, a theory that turns our understanding of reality on its head. The holographic principle emerged from the intersection of string theory and quantum gravity, two of the most ambitious attempts to unify the laws of physics. At its core, the theory suggests that all the information needed to describe our three-dimensional universe can be encoded on a two-dimensional boundary, much like how a hologram stores a 3D image on a flat surface. It's a radical idea, but one that could provide profound insights into the universe's accelerating expansion. How does this connect to dark energy and the cosmos's rapid growth? According to the holographic principle, the universe's expansion might not be driven by forces within our three-dimensional reality, but by processes happening in these hidden higher dimensions. Think of it like watching a movie projected onto a screen. The action you see, the explosions, the sweeping landscapes isn't happening on the screen itself, but is being created by a projector hidden behind the scenes. In the same way, the holographic principle suggests that the universe's expansion could be a projection of deeper, more fundamental processes occurring in a realm we can't directly observe. This theory also offers a potential solution to one of the biggest puzzles in physics, the nature of space and time. If the universe is indeed a hologram, then space-time itself might not be fundamental but rather an emergent property, something that arises from the interactions of information encoded on this two-dimensional surface. It's a concept that challenges everything we thought we knew about the fabric of reality, suggesting that the universe is far more interconnected and layered than we ever imagined. But the holographic principle doesn't just stop at explaining the universe's structure. It also opens the door to new ways of thinking about its ultimate fate. If the universe is a projection, could changes in the source code on the two-dimensional boundary lead to shifts in how the cosmos behaves? Could this explain why the universe's expansion is accelerating? These are questions that push the boundaries of our understanding, inviting us to consider possibilities that once seemed beyond the realm of science. As intriguing as the holographic principle is, it's not the only theory that challenges our perception of reality. What if the universe we see is just one of countless others, each with its own set of physical laws and properties? That brings us to the multiverse hypothesis, a concept that takes the idea of hidden dimensions and scales it up to an almost unimaginable level. What if our universe isn't the only one? What if it's just a single bubble in a vast cosmic sea, one of countless others, each with its own unique set of physical laws and properties? This is the multiverse hypothesis, a theory that stretches our imagination to its limits and offers a bold new perspective on why our universe is accelerating. In this framework, our universe is just one of many, perhaps an infinite number of universes, each existing in its own pocket of space-time. These universes could have wildly different physical constants, from the strength of gravity to the density of dark energy. Some might collapse in on themselves almost immediately, while others could expand so rapidly that stars and galaxies never form. In this cosmic lottery, our universe is a rare winner, one where dark energy's density is just right to allow galaxies to form, life to emerge, and us to ponder its mysteries. Imagine walking into a casino with an endless row of slot machines, each representing a different universe. You pull the lever on one, and the symbols that line up determine the physical laws of that universe. In most cases, the result might be chaotic or inhospitable, a universe that collapses instantly or expands too quickly for anything to form. But every now and then, you hit the jackpot, a universe with just the right balance of forces to sustain complexity and life. That's the kind of cosmic chance the multiverse hypothesis suggests might explain our universe's accelerating expansion. This idea isn't just a flight of fancy. It's grounded in some of the most cutting-edge theories in physics, including string theory and inflationary cosmology. According to these models, the conditions of the early universe could have given rise to a process called eternal inflation, where new universes are constantly being born, each with its own unique properties. In this vast multiverse, our universe's acceleration becomes less of a mystery and more of a statistical inevitability, one of countless possible outcomes in a cosmic landscape of infinite variety. But the multiverse hypothesis also raises profound questions. If there are other universes out there, could they ever interact with ours? And if our universe's properties are the result of chance, what does that mean for the laws of physics as we know them? Some scientists argue that the multiverse could provide a natural explanation for why dark energy's density is so finely tuned, while others see it as a philosophical leap that pushes the boundaries of what science can test. As we grapple with these ideas, one thing becomes clear. The multiverse hypothesis challenges us to think bigger than ever before. It invites us to consider not just the nature of our universe, but the very fabric of reality itself. And yet, even as we explore these vast cosmic possibilities, there's another theory that brings us back to the heart of our own universe, to the very fabric of space and the energy that might be driving its expansion. That brings us to the role of vacuum energy, a concept that ties together some of the most fundamental ideas in physics. Empty space isn't as empty as it seems. In fact, according to quantum mechanics, even the void is alive with activity, a seething, invisible sea of energy that never rests. This is vacuum energy, a concept that takes us deep into the quantum realm, where particles pop in and out of existence in a dance so fleeting, it defies our everyday understanding of reality. But what if this hidden energy isn't just a quirk of the quantum world? What if it's the key to understanding why the universe is expanding faster and faster? To grasp this idea, picture a radio tuned to a frequency where no station is broadcasting. Instead of silence, you hear a faint, crackling static, a background hum that fills the airwaves. This static is a bit like vacuum energy, a constant underlying presence that's always there, even when everything else seems quiet. In the quantum world, this energy arises from fluctuations, tiny, rapid changes in the field of space itself. These fluctuations are so small, they're almost imperceptible, but they add up to create a force that could be driving the universe's accelerating expansion. The connection between vacuum energy and the cosmos's rapid growth lies in Einstein's equations of general relativity. In these equations, vacuum energy acts like a kind of pressure, pushing space apart rather than pulling it together. It's as if the universe is filled with an invisible spring, constantly stretching the fabric of space-time. Over billions of years, this pressure could explain why galaxies are racing away from each other at ever-increasing speeds. But here's where things get tricky. When physicists try to calculate how much vacuum energy exists, they run into a problem so stark, It's been called the vacuum catastrophe. According to quantum theory, the energy density of the vacuum should be astronomically high, so high that it would have ripped the universe apart long before galaxies could form. Yet when we look at the cosmos, we see that dark energy's influence is incredibly subtle, billions of times weaker than what quantum mechanics predicts. It's like expecting a tidal wave but finding only a ripple. This enormous discrepancy has left scientists scratching their heads. Why is the observed value of vacuum energy so much smaller than the theoretical prediction? Is there a flaw in our understanding of quantum mechanics, or are we missing something fundamental about the nature of space itself? Some researchers suggest that unknown mechanisms might be cancelling out most of the vacuum energy, leaving only a tiny fraction to influence the universe. Others propose that our current theories need a complete overhaul, pointing to the possibility of new physics beyond the standard model. Despite these challenges, the idea of vacuum energy offers a fascinating link between the quantum world and the cosmos. It's a reminder that the very small and the very large are deeply connected, with phenomena on the tiniest scales shaping the fate of the entire universe. And as we grapple with the mysteries of vacuum energy, another intriguing possibility emerges, one that takes the concept of cosmic acceleration to an even more extreme level. What if dark energy isn't just a gentle push, but a force that grows stronger over time, eventually overwhelming everything in its path? This is the basis of phantom energy, a theory that imagines a universe on the brink of a dramatic and catastrophic end. But to understand how this could happen, we'll need to explore the darker side of dark energy and the potential futures it might bring. Phantom energy takes the concept of dark energy to an extreme and not a comforting one. Imagine a force so powerful, so relentless, that it doesn't just push the universe apart, but does so with such ferocity that it could eventually tear everything within it to shreds. This is the chilling possibility behind phantom energy, a hypothetical form of dark energy with a negative equation of state. Unlike the gentle hum of the cosmological constant or the dynamic ebb and flow of quintessence, phantom energy grows stronger over time, accelerating the universe's expansion at an ever-increasing rate. Picture a runaway train barreling down a steep mountainside, its speed building uncontrollably as it hurtles toward disaster. Now replace the train with the universe and the mountainside with the fabric of space-time. Phantom energy is the force pushing that train faster and faster, until the tracks themselves, the very structure of reality, begin to buckle and break. In this scenario, galaxies wouldn't just drift apart, they'd be ripped apart. Stars, planets, even atoms, everything would be torn asunder in a catastrophic event known as the Big Rip. The Big Rip isn't just a dramatic end to the universe, it's a complete unraveling of existence. As phantom energy grows stronger, it would overcome every force that holds matter together. Gravity, electromagnetism, even the nuclear forces binding atomic nuclei. First, galaxies would be pulled apart, then solar systems, then planets, and finally, molecules and atoms themselves. The universe would end not with a collapse or a freeze, but with a violent, all-consuming tear. It's a fate so extreme, it's hard to even fathom, yet it's a real possibility if phantom energy exists. What makes this theory so unsettling is its inevitability. Unlike other models of the universe's fate, which might play out over unimaginably long timescales, the Big Rip could happen relatively quickly within tens of billions of years. For context, that's not much longer than the current age of the universe. If phantom energy is real, we could be living in a cosmic countdown, hurtling toward an end that's as sudden as it is devastating. But phantom energy isn't just a doomsday scenario, it's also a fascinating challenge to our understanding of physics. If this force exists, it would require a complete rethinking of how energy and space interact. Why would dark energy grow stronger over time? What mechanism could drive such a dramatic change? And how does this fit with our observations of the universe so far? These are questions that push the boundaries of cosmology, forcing us to confront the possibility that the cosmos is far more volatile than we ever imagined. As we grapple with the implications of phantom energy, another intriguing question arises. Could the answer to the universe's accelerating expansion lie not within our three-dimensional reality, but in dimensions we can't yet perceive? This brings us to the idea of extra dimensions, a concept that takes us into the realm of string theory and beyond. What if the universe we see is just a slice of something much larger, like a shadow cast by an object we can't fully perceive? This is the mind-bending idea behind theories of extra dimensions, where our familiar three-dimensional world might be just the surface of a deeper, more complex reality. In string theory and brain cosmology, scientists propose that our universe could be a brain, a kind of membrane floating within a higher dimensional space. These extra dimensions, hidden from our view, could hold the key to understanding why the cosmos is expanding at an ever-increasing rate. To visualize this, imagine a flat piece of paper floating in a room. The paper represents our universe, while the room itself is a higher dimensional space. Now, imagine gravity as a force that doesn't just stay on the paper but leaks into the room, spreading out into those extra dimensions. This leakage could explain why gravity appears weaker in our universe than other fundamental forces. It's not disappearing. It's simply spreading out where we can't see it. But how does this connect to the universe's accelerating expansion? Some theories suggest that the energy driving this acceleration could come from interactions between our brain and other brains in higher dimensional space. Picture two sheets of paper floating in the same room, occasionally brushing against each other. These interactions could create ripples or energy transfers that manifest in our universe as dark energy, pushing galaxies apart faster and faster. This idea also offers a fascinating way to reinterpret dark energy. Instead of being a mysterious force within our three-dimensional universe, it might be a shadow of something happening in higher dimensions, a kind of cosmic echo from a realm we can't directly observe. It's like seeing the ripples on the surface of a pond and realizing they're caused by something moving beneath the water. Brain cosmology doesn't just challenge our understanding of gravity and dark energy, it reshapes how we think about the universe itself. If extra dimensions exist, they could explain not only the cosmos's accelerating expansion but also other mysteries, like the nature of dark matter or the unification of fundamental forces. It's a bold reimagining of reality, one that takes us beyond the limits of our everyday experience. As we explore these higher dimensional possibilities, another intriguing question arises. What if the universe's expansion isn't a one-way journey, but part of an endless cycle of creation and destruction? That brings us to our next theory, which imagines a cosmos that breathes, expanding and contracting in an eternal rhythm. What if the universe isn't a one-time event, but part of an eternal rhythm, a cosmic heartbeat that pulses with expansion and contraction over and over again? This is the essence of the cyclic universe model, a theory that imagines our cosmos not as a single, linear story, but as an endless loop of creation and renewal. In this framework, the universe we see today is just one chapter in an infinite saga, where each cycle begins with a big bang, expands, and eventually contracts, only to start all over again. Think of it like the changing seasons. Just as spring gives way to summer, then fall, and finally winter, the cyclic universe model suggests that the cosmos has its own natural rhythm. Right now, we're in the summer phase, a period of rapid expansion driven by dark energy. But eventually, this expansion could slow, reverse, and lead to a winter of contraction, where the universe collapses back in on itself. And just as winter eventually turns to spring, this collapse could trigger a new Big Bang, starting the cycle anew. One of the most intriguing aspects of this model is how it reinterprets dark energy. Instead of being a mysterious force pushing the universe apart indefinitely, dark energy could play a crucial role in transitioning the cosmos from one cycle to the next. It might act like a cosmic clock, winding down the current phase of expansion and setting the stage for the next cycle to begin. In this way, dark energy isn't just a driver of the universe's acceleration, it's a key player in its eternal renewal. But how could the universe contract after expanding so dramatically? Some versions of the cyclic model propose that dark energy's influence might weaken over time, allowing gravity to eventually take over and pull everything back together. Others suggest that the universe's expansion could reach a point where it triggers a quantum phase transition, a kind of cosmic reset button that flips the universe into a new state, ready to begin again. This idea isn't just poetic, it's grounded in some of the most advanced theories in physics, including string theory and brane cosmology. In these frameworks, the collisions of higher dimensional branes could act as the cosmic equivalent of a heartbeat, driving the cycles of expansion and contraction. It's a vision of the universe that's both awe-inspiring and humbling, reminding us that our existence might be just one moment in an infinite cosmic dance. Yet, as compelling as the cyclic universe model is, it's not without its challenges. For one, it requires a mechanism to prevent the universe from becoming more disordered with each cycle, a problem known as the entropy crisis. If entropy, the measure of disorder, keeps increasing, how could the universe reset itself without losing its structure? Some theorists suggest that quantum effects or new physics might offer a solution, but these ideas remain speculative for now. The cyclic universe model also raises profound questions about the nature of time. If the universe is truly cyclical, does time itself loop back on itself? Or is each cycle a completely new beginning with no connection to the past? These are questions that push the boundaries of our understanding, challenging us to think beyond the linear flow of time we experience in our daily lives. As we explore these ideas, it's clear that the cyclic universe model offers a radically different perspective on the cosmos. But it's not the only way to approach the mystery of the universe's accelerating expansion. What if the key lies not in the grand cycles of time, but in the small-scale irregularities scattered throughout the cosmos? That brings us to our next theory, which examines how the uneven distribution of matter in the universe might be shaping its fate. When we look out into the universe, it's easy to think of it as a smooth, uniform expanse with galaxies scattered evenly like glitter on a canvas. But the truth is far more intricate and far messier. The cosmos is full of irregularities, from dense galaxy clusters to vast, empty voids, creating a patchwork of matter and emptiness on the largest scales. This uneven distribution, known as inhomogeneity, might hold the key to one of the universe's greatest mysteries, its accelerating expansion. Inhomogeneous cosmology is a theory that suggests these cosmic irregularities could be influencing how the universe expands, creating the illusion of acceleration without the need for dark energy. Think of it like driving on a bumpy road. If you're in a car moving over smooth pavement, your speed feels steady and predictable. But when the road becomes uneven with hills, dips, and potholes, your speedometer might fluctuate, making it seem like you're accelerating or decelerating even if your engine's power stays the same. In the universe, these bumps are the dense clusters of galaxies, while the dips are the vast voids. As space expands, light traveling through these regions takes different paths, which could make it appear as though the expansion is speeding up. This idea challenges the conventional view that dark energy is the sole driver of cosmic acceleration. Instead, It suggests that the universe's complex structure could be playing tricks on us, distorting our observations in ways we're only beginning to understand. If inhomogeneities are responsible, it would mean that the universe isn't expanding faster because of a mysterious force, but because we're seeing the effects of its lumpy, uneven nature on a grand scale. However, this theory isn't without its challenges. Modeling the universe's inhomogeneous structure is an incredibly complex task, requiring precise calculations of how matter is distributed across billions of light years. Even with supercomputers, accurately simulating these irregularities is a daunting challenge. And while inhomogeneous cosmology offers an intriguing alternative to dark energy, it still struggles to explain some key observations, such as the precise details of the cosmic microwave background radiation or the large-scale distribution of galaxies. Despite these hurdles, the theory has sparked important conversations about how we interpret the universe's expansion. It reminds us that the cosmos is far from uniform, and that its complexity might hold answers we've yet to uncover. Could the universe's acceleration be a cosmic illusion, shaped by the uneven distribution of matter, or is dark energy still the most compelling explanation? As we wrestle with these questions, another fascinating possibility emerges, one that shifts our focus from the large-scale structure of the universe to the very laws that govern it. What if the constants of nature, like the speed of light or the strength of gravity, aren't constant at all? What if they change over time, subtly shaping the universe's evolution? That brings us to our next theory, which explores the idea of time-varying fundamental constants and their potential role in the cosmos's accelerating expansion. What if the very rules of the universe aren't set in stone? What if the constants we rely on, like the speed of light, the strength of gravity, or the charge of an electron, are more like variables subtly shifting over time? This is the intriguing possibility behind the theory of time-varying fundamental constants, a concept that challenges one of the most fundamental assumptions in physics, that the laws governing the cosmos are eternal and unchanging. Imagine a clock that doesn't tick at a steady pace. Sometimes it speeds up, other times it slows down, but never in a way that's easily noticeable. This is how time-varying constants might work. The speed of light, for example, could have been faster in the early universe, or the gravitational constant might be gradually weakening over billions of years. These changes, though incredibly subtle, could have profound effects on how the universe evolves, including its accelerating expansion. If fundamental constants aren't constant, it could explain why the universe is expanding faster than expected. For instance, if gravity were weakening over time, its pull on galaxies would decrease, allowing them to drift apart more rapidly. Similarly, a changing speed of light could alter the way energy and matter interact on cosmic scales, potentially creating the illusion of dark energy. It's a radical idea, but one that could solve some of the biggest puzzles in modern cosmology without invoking mysterious forces or unseen dimensions. But how could we detect such changes? Measuring the speed of light or the strength of gravity with the precision needed to spot tiny variations is no small feat. Scientists have turned to some of the most distant objects in the universe for answers. By studying the light from ancient quasars and analyzing the spectra of faraway galaxies, researchers can compare the values of fundamental constants billions of years ago to those we measure today. So far, the evidence suggests that any variations, if they exist, are incredibly small, but the search continues, driven by the tantalizing possibility that our understanding of the universe's laws might need a rewrite. The implications of time-varying constants go far beyond cosmic expansion. If these fundamental values can change, it could mean that the laws of physics themselves are not fixed but are instead shaped by deeper, underlying principles we've yet to uncover. It's a humbling thought, reminding us that even the most basic aspects of reality might be more fluid than we ever imagined. As we explore this theory, another fascinating idea emerges, one that takes us from the subtle shifts of fundamental constants to the dramatic structures that might weave through the fabric of space-time. What if the universe is threaded with cosmic strings, unimaginably thin strands of energy left over from the Big Bang? These cosmic strings could be the scars of the early universe, and their effects might hold clues to the cosmos's accelerating expansion. But to understand how, we'll need to step into a world where space itself is filled with ripples and knots. Picture a frozen lake on a cold winter's day. The surface is smooth and solid, but as the temperature fluctuates, cracks begin to form, thin, jagged lines that snake across the ice. Now, imagine that these cracks aren't just on the surface of a lake, but woven through the very fabric of space-time itself. This is the essence of cosmic strings, hypothetical one-dimensional defects that could be threading the universe like invisible scars left over from the Big Bang. These cosmic strings are thought to be unimaginably thin, yet unbelievably dense, carrying vast amounts of energy within their minuscule width. And while they've never been directly observed, their existence could hold profound implications for how we understand the universe's accelerating expansion. Cosmic strings are a type of topological defect, a kind of cosmic knot, that forms when the universe undergoes a phase transition, much like water freezing into ice. In the early moments of the cosmos, as the universe cooled and expanded, rapid changes in its fundamental properties might have created these defects. Think of them as the cosmic equivalent of cracks in a frozen lake, imperfections that arise when something shifts too quickly. But unlike the cracks in ice, cosmic strings aren't just static flaws. They're dynamic, vibrating and moving through space, potentially influencing the universe on the largest scales. So, how could these tiny, thread-like structures affect the universe's expansion? One possibility is that cosmic strings might contribute to dark energy, the mysterious force driving the acceleration. As they stretch and vibrate, they could release energy into the fabric of space-time, subtly pushing galaxies apart. Another idea is that their gravitational influence might alter the dynamics of cosmic acceleration, creating ripples in space-time that affect how the universe evolves over time. It's like throwing a pebble into a pond. The ripples spread out, subtly changing the surface in ways that might not be immediately obvious. Detecting cosmic strings, however, is no easy task. They're incredibly thin, just one atom's width across, but can stretch across vast cosmic distances. Their energy density makes them detectable in theory, but their elusive nature means we'd need incredibly precise instruments to spot them. One promising method involves looking for their gravitational effects, such as distortions in the light from distant galaxies or ripples in the cosmic microwave background. These subtle signatures could reveal their presence, offering a glimpse into the universe's earliest moments and the forces that shaped it. While cosmic strings remain hypothetical, they're a tantalizing possibility that bridges the gap between the quantum world and the cosmos at large. They remind us that even the tiniest imperfections in the fabric of reality can have far-reaching consequences, shaping the universe in ways we're only beginning to understand. But cosmic strings aren't the only way to approach the mystery of cosmic acceleration. What if the answer lies not in defects in space-time, but in the very nature of gravity itself? That brings us to the idea of entropic gravity, a theory that reimagines gravity not as a fundamental force, but as an emergent property of the universe's underlying structure. What if gravity isn't a fundamental force at all, but something that emerges from the universe's natural tendency toward disorder? This is the intriguing idea behind entropic gravity, a theory that reimagines one of the most familiar forces in nature as a byproduct of entropy, the measure of disorder in a system. Instead of seeing gravity as a force that pulls objects together, entropic gravity suggests it's more like a cosmic tendency, a side effect of the universe's drive to maximize entropy. To understand this, think of a hot cup of coffee sitting on a table. Over time, the heat from the coffee spreads out into the surrounding air, increasing the system's overall entropy. In entropic gravity, something similar happens with space and matter. As the universe evolves, it seeks to maximize entropy, and this drive creates what we perceive as gravity. It's as if the fabric of space-time is constantly adjusting itself to create the most disordered state possible, and this process manifests as the force we call gravity. This perspective offers a radical new way to think about cosmic acceleration. If gravity emerges from entropy, then the universe's expansion might not need dark energy to explain its speeding up. Instead, the increase in entropy over time could naturally lead to the stretching of space, pushing galaxies apart as the cosmos strives for greater disorder. It's a concept that ties together thermodynamics and gravity, two pillars of physics that have traditionally been seen as separate. One of the most compelling aspects of entropic gravity is how it reframes our understanding of the universe's evolution. Rather than relying on mysterious forces or unseen dimensions, it suggests that the cosmos is simply following a natural tendency toward disorder, a principle that governs everything from the behavior of molecules to the motion of galaxies. But this theory isn't without its challenges. Critics argue that entropic gravity struggles to explain certain observations, such as the precise details of galaxy rotation curves or the behavior of black holes. And while it offers a fresh perspective on gravity, it doesn't yet provide a complete framework to replace our current understanding of the force. Still, it's a fascinating idea that pushes us to think differently about the nature of reality. As we explore the concept of entropic gravity, another intriguing question arises. What if the universe's expansion is influenced not just by thermodynamics, but by the strange, counterintuitive world of quantum mechanics? That brings us to the role of quantum entanglement, a phenomenon that links particles across vast distances and might hold clues to the cosmos's accelerating growth. At the heart of quantum mechanics lies one of the most baffling and beautiful phenomena in science, quantum entanglement. This strange connection between particles where the state of one instantly influences another, no matter how far apart they are, seems to defy the very fabric of space and time. But what if this entanglement isn't just a quirk of the quantum world? What if it's woven into the very structure of the universe, shaping its expansion in ways we're only beginning to understand? Picture a vast, invisible web stretching across the cosmos, its threads connecting every particle to countless others. These threads aren't made of matter or energy, they're the bonds of quantum entanglement, linking distant parts of the universe in an intricate network. Now imagine that this web isn't static. As the universe expands, these connections stretch and pull, subtly influencing the way space itself evolves. This is the speculative idea behind the theory that quantum entanglement might play a role in cosmic acceleration. In this framework, entanglement isn't just a microscopic oddity, it's a cosmic force. Just as gravity shapes the large-scale structure of the universe, entanglement could create a hidden architecture that affects how galaxies move and space stretches. Some scientists suggest that this network of connections might even contribute to dark energy, the mysterious force driving the universe's accelerating expansion. It's as if the universe is held together not just by gravity, but by an invisible lattice of quantum bonds, each one tugging and pulling in ways we can't yet fully measure. But how could something so small-scale influence something as vast as the cosmos? The key lies in the sheer scale of entanglement. In the quantum world, particles are constantly entangling and disentangling, creating a dynamic, ever-changing network. Over billions of years, these interactions could add up, creating a cumulative effect that shapes the universe on the largest scales. It's like the way countless tiny ripples on a pond can combine to form a wave, a small but persistent influence that grows over time. This theory is still highly speculative, and many questions remain. How exactly does entanglement affect the expansion of space? Could it really explain the observed acceleration, or is it just one piece of a much larger puzzle? And perhaps most intriguingly, what does this mean for our understanding of space and time? If entanglement is shaping the cosmos, it suggests that the universe is far more interconnected than we ever imagined, with every particle playing a role in its grand design. As we explore this idea of quantum entanglement, another fascinating possibility emerges, one that shifts our focus from the bonds between particles to the very nature of space itself. What if space-time isn't a fundamental feature of the universe, but something that emerges from deeper, more fundamental processes? This is the essence of emergent space-time, a theory that reimagines the fabric of reality in a way that could reshape our understanding of cosmic acceleration. What if space and time aren't the foundation of reality, but something that emerges from a deeper, more fundamental layer of existence? This is the mind-bending idea behind emergent spacetime, a theory that reimagines the very fabric of the universe as a dynamic, evolving construct rather than a fixed stage. Instead of viewing spacetime as a fundamental feature, this theory suggests it's more like a tapestry woven together from countless quantum threads, each one representing a tiny, indivisible piece of the cosmos. To grasp this concept, picture a piece of fabric. From a distance, it appears smooth and continuous, but up close, you can see the individual threads that make it up. In the same way, spacetime might seem like a seamless, unchanging backdrop to our lives, but at its core, it could be built from quantum processes so small and intricate, they're beyond our current ability to observe. These processes, acting together, create the illusion of a continuous, flowing space and time, a kind of cosmic illusion born from the interactions of countless quantum elements. So, how does this connect to the universe's accelerating expansion? If spacetime is emergent, it means it's not static but dynamic, constantly evolving as the underlying quantum processes shift and change. This could explain why the universe is stretching faster and faster, because spacetime itself is growing, expanding, and reshaping as these quantum threads interact. In this view, dark energy might not be a mysterious force pushing the universe apart, but a natural consequence of the way spacetime emerges from its quantum foundations. One way to think about this is to imagine spacetime as a living, breathing entity. Just as a tree grows from a seed, expanding and changing over time, spacetime could be evolving in ways we don't yet fully understand. This perspective challenges the idea of a fixed, unchanging cosmos, suggesting instead that the universe is a dynamic, ever-shifting reality, one where space and time are not constants, but variables shaped by deeper, unseen processes. Emergent spacetime also offers a potential solution to one of the biggest puzzles in physics: how to reconcile quantum mechanics, which governs the tiny world of particles, with general relativity, which describes the large-scale structure of the universe. If spacetime itself emerges from quantum interactions, it could provide a bridge between these two seemingly incompatible frameworks, offering a unified picture of reality that spans the smallest particles to the largest galaxies. Yet, as intriguing as this theory is, it raises profound questions about the nature of existence. If spacetime is emergent, what lies beneath it? Are there deeper layers of reality waiting to be discovered? And how does this dynamic, evolving spacetime affect our understanding of time? Is it still a linear progression or something far more complex? As we explore these questions, another fascinating possibility emerges, one that shifts our focus from the quantum threads of spacetime to the colossal structures that might shape the cosmos, black holes. These enigmatic objects, with their immense gravitational pull, could play a surprising role in the universe's accelerating expansion. But to understand how, we'll need to venture into the mysterious world of singularities and event horizons, where the laws of physics as we know them begin to break down. Black holes are often thought of as cosmic vacuums, sucking in everything around them with their immense gravitational pull. But what if these enigmatic objects are doing more than just consuming matter? What if they're also playing a role in the universe's accelerating expansion? This is the intriguing possibility behind the idea that black holes could be connected to dark energy, the mysterious force driving the cosmos apart at an ever-increasing rate. To understand this, think of black holes not just as gravitational traps, but as cosmic batteries. Just as a battery stores and releases energy, black holes might be storing vast amounts of energy within their event horizons, the boundary beyond which nothing, not even light, can escape. Over time, this stored energy could be subtly released, influencing the fabric of space-time in ways that contribute to the universe's expansion. It's a bit like a slow leak in a tire. You might not notice it at first, but over time, it changes the way the tire behaves. This theory is still highly speculative, but it's rooted in some fascinating ideas from both general relativity and quantum mechanics. For instance, black holes are thought to emit something called Hawking radiation, a faint glow of particles that escape from their boundaries due to quantum effects. This radiation suggests that black holes aren't entirely closed systems. They're slowly losing energy, and that energy has to go somewhere. Could it be contributing to the dark energy that's pushing the universe apart? Another angle comes from the way black holes warp space-time. Their immense gravity creates deep wells in the fabric of the cosmos, and as they move and interact, these wells could create ripples that subtly affect the universe's expansion. Imagine dropping a heavy ball into a pool of water. The ripples spread out, influencing the water's surface in ways that linger long after the ball has settled. In the same way, black holes might be sending out gravitational waves or other effects that ripple through space, contributing to the overall dynamics of the cosmos. Of course, this theory raises plenty of questions. How exactly would black holes store or release energy on a scale large enough to affect the universe's expansion? And how does this fit with our current understanding of dark energy? While the answers aren't clear yet, the idea that black holes could play a role in cosmic acceleration is a reminder of how interconnected the universe might be and how much we still have to learn. This exploration of black holes and their potential connection to dark energy leads us to another intriguing idea. What if the universe isn't expanding indefinitely, but instead cycles through periods of expansion and contraction? This is the essence of the bouncing universe model, a theory that imagines the cosmos not as a one-time event, but as a series of cosmic rebounds, each one reshaping the fabric of reality in profound ways. What if the universe isn't a one-way journey, but part of an eternal cycle, a cosmic rhythm of expansion and contraction that repeats over and over again? This is the essence of the bouncing universe model, a theory that reimagines the cosmos not as a single linear story, but as an endless loop of birth, growth, collapse, and rebirth. In this framework, the Big Bang wasn't the beginning of everything, but just one moment in an infinite series of cosmic rebounds. Imagine the universe as a cosmic heartbeat, pulsing with the rhythm of expansion and contraction. Each beat begins with a Big Bang, followed by a period of rapid growth driven by dark energy. Galaxies form, stars ignite, and life emerges, until the universe reaches its peak expansion. Then, like a heartbeat slowing after exertion, the cosmos begins to contract, pulled back together by gravity. Galaxies draw closer, stars fade, and eventually everything collapses into a dense, hot state. But instead of ending there, the universe bounces back, reigniting in a new Big Bang and starting the cycle all over again. This idea isn't just poetic, it's rooted in some of the most advanced theories in physics. The bouncing universe model draws from concepts in string theory, loop quantum gravity, and even general relativity to suggest that the universe could avoid a singular Big Bang altogether. Instead of a single point of infinite density, the bounce represents a transition, a moment where the universe's collapse reverses, leading to a new phase of expansion. One of the most intriguing aspects of this model is how it reinterprets dark energy. Instead of being a mysterious force pushing the universe apart indefinitely, dark energy could play a crucial role in the cosmic rhythm, acting like a cosmic spring that helps transition the universe from contraction to expansion. During the expansion phase, dark energy drives galaxies apart at an accelerating rate. But as the universe begins to contract, its influence might weaken, allowing gravity to take over and pull everything back together. Then, as the cosmos reaches its densest point, dark energy could reassert itself, triggering the next bounce and starting the cycle anew. This idea also offers a fascinating way to think about the universe's ultimate fate. Unlike theories that predict an endless expansion or a catastrophic collapse, the bouncing universe model suggests a more balanced, cyclical future. It's a vision of the cosmos that's both awe-inspiring and comforting, reminding us that even the grandest processes in the universe might follow natural, repeating patterns. Yet, as compelling as this theory is, it's not without its challenges. For one, it requires a mechanism to prevent the universe from becoming more disordered with each cycle, a problem known as the entropy crisis. If entropy, the measure of disorder, keeps increasing, how could the universe reset itself without losing its structure? Some theorists suggest that quantum effects or new physics might offer a solution, but these ideas remain speculative for now. The bouncing universe model also raises profound questions about the nature of time. If the universe is truly cyclical, does time itself loop back on itself? Or is each cycle a completely new beginning with no connection to the past? These are questions that push the boundaries of our understanding, challenging us to think beyond the linear flow of time we experience in our daily lives. As we explore these ideas, it's clear that the bouncing universe model offers a radically different perspective on the cosmos. But it's not the only way to approach the mystery of the universe's accelerating expansion. What if the key lies not in the grand cycles of time, but in the subtle forces that permeate the fabric of space itself? That brings us to our next theory, which examines the role of scalar fields, a concept that could redefine our understanding of dark energy and the forces shaping the universe. Picture an invisible wind sweeping through the cosmos, shaping everything in its path without ever being seen. This is the essence of scalar fields, hypothetical forces that could be subtly influencing the universe's accelerating expansion. Unlike familiar forces like gravity or electromagnetism, scalar fields are theorized to permeate all of space, filling the cosmos with an unseen energy that might be driving galaxies apart faster and faster. These fields are like the ocean currents of the universe, hidden, yet powerful enough to steer the motion of everything within it. At their core, scalar fields are mathematical constructs, but they're also a tantalizing possibility for explaining dark energy. Imagine a field that stretches across the entire universe, its energy fluctuating over time. In some regions, it might push space apart gently, while in others, it could create ripples that mimic the effects of dark energy. This flexibility makes scalar fields a compelling alternative to the cosmological constant, offering a dynamic explanation for why the universe's expansion is speeding up. One of the most intriguing aspects of scalar fields is how they might interact with matter and radiation. Unlike dark energy, which is often described as a static force, scalar fields could change over time, influencing the cosmos in ways that evolve as the universe grows. For instance, a scalar field might have been stronger in the early universe, driving rapid expansion but weaker today, explaining why dark energy's effects are so subtle. It's like a cosmic thermostat, adjusting the universe's expansion rate as needed. But how could we detect something so elusive? Scalar fields, by their nature, don't interact directly with light or matter in ways we can easily observe. Instead, scientists look for indirect evidence, such as subtle changes in the cosmic microwave background or the distribution of galaxies across the universe. These observations could reveal the fingerprints of scalar fields, showing how they've shaped the cosmos over billions of years. Scalar fields also hold the potential to unify physics in ways that go beyond dark energy. Some theories suggest that these fields could bridge the gap between quantum mechanics and general relativity, offering a deeper understanding of how the universe works at both the smallest and largest scales. It's a bold idea, but one that could reshape our understanding of reality. As we explore the possibilities of scalar fields, another fascinating question arises. What if the vacuum of space itself isn't empty, but filled with energy that's slowly decaying over time? This idea brings us to the concept of a decaying vacuum, a theory that imagines the universe's expansion as a side effect of space itself losing energy. But to understand how this works, we'll need to venture into the strange world of quantum fields and the ever-changing nature of the cosmos. What if the energy fueling the universe's expansion is slowly fading away, like a dimming light bulb that once burned brightly? This is the intriguing possibility behind the theory of decaying vacuum energy, which suggests that the mysterious force driving the cosmos apart might not be constant but gradually weakening over time. In this scenario, the vacuum of space, often thought of as empty, is actually filled with energy that's slowly dissipating, subtly altering the universe's expansion rate as it does so. To picture this, imagine a vast, glowing lantern illuminating a dark room. At first, its light is steady and strong, casting a clear, bright glow. But as time passes, the light begins to dim, growing fainter and fainter until it's barely noticeable. In the same way, decaying vacuum energy suggests that the universe's expansion is powered by a force that's gradually losing strength, like a cosmic battery running out of charge. This could explain why the cosmos is stretching faster now than it did in the past, because the energy driving that expansion is slowly fading away. This theory offers a fresh perspective on dark energy, proposing that it's not a static force but one that evolves over time. Instead of a constant push, vacuum energy might have been stronger in the early universe, driving rapid expansion, but is now weakening, leading to the more subtle acceleration we observe today. It's a concept that ties the universe's past to its future, suggesting that the cosmos is shaped not just by the forces at play now, but by how those forces have changed over billions of years. The implications of decaying vacuum energy are profound. If this energy continues to weaken, the universe's expansion might eventually slow down, leading to a future where galaxies drift apart more gently. Or if the energy decays completely, the cosmos could enter a phase where gravity takes over, pulling everything back together in a dramatic collapse. It's a cosmic balancing act where the fate of the universe hinges on the delicate interplay between fading energy and the relentless pull of gravity. But how could we test such a theory? One approach is to look for subtle changes in the universe's expansion rate over time. By studying distant supernova, galaxy clusters, and the cosmic microwave background, scientists can track how the cosmos has evolved and whether the effects of dark energy have changed. These observations could reveal whether vacuum energy is indeed decaying, offering a fascinating glimpse into the universe's long-term trajectory. As we ponder the idea of a fading vacuum energy, another thought-provoking question arises. Could the universe's accelerating expansion be shaped not just by physical forces, but by the very fact that we exist to observe it? This brings us to our final theory, which explores the role of anthropic reasoning, a concept that ties the cosmos's behavior to the conditions necessary for life to emerge. What if the universe's accelerating expansion isn't just a random cosmic quirk, but a necessary condition for our very existence? This is the fascinating idea behind anthropic reasoning, a theory that suggests the universe's properties, including its accelerating expansion, are finely tuned to allow life to emerge. In other words, the cosmos isn't just expanding faster by chance. It's doing so because in a universe that didn't accelerate, we wouldn't be here to observe it. Think of it like a tailor crafting a suit. If the suit isn't made to fit the wearer perfectly, it won't serve its purpose. In the same way, the universe might be tailor-made with just the right conditions, like the precise strength of dark energy, to allow complex structures like galaxies, stars, and ultimately life to form. If the universe had expanded too quickly or too slowly, the delicate balance needed for life would have been disrupted, leaving the cosmos empty and lifeless. It's a perspective that shifts the question from, why is the universe expanding this way, to, could it have expanded any other way and still allowed us to exist? This line of thinking, known as the Anthropic Principle, raises profound philosophical questions. If the universe's properties are fine-tuned for life, does that imply a deeper purpose or design? Or is it simply a matter of probability where countless universes exist with different properties, and we happen to live in one where the conditions are just right? This idea ties closely to the multiverse hypothesis, which suggests that our universe might be one of many, each with its own unique set of physical laws. In this vast cosmic landscape, it's no surprise that at least one universe would have the precise conditions needed for life to arise. But anthropic reasoning isn't just a philosophical thought experiment, it's also a practical tool for scientists. By recognizing that our observations of the universe are inherently biased by the fact that we exist to make them, researchers can refine their theories and predictions. For example, if dark energy were significantly stronger, galaxies might never have formed, making our existence impossible. This realization helps explain why the observed value of dark energy is so small and subtle. It's the only value compatible with a universe that can support life. Still, this theory isn't without its critics. Some argue that anthropic reasoning risks being a cop-out, a way to avoid explaining why the universe has the properties it does. Others question whether it's even possible to test such ideas scientifically. After all, if we can only observe one universe, our own, how can we ever know if others exist with different properties? These debates highlight the tension between science and philosophy, reminding us that some questions might lie beyond the reach of empirical investigation. Yet, as we reflect on the implications of anthropic reasoning, one thing becomes clear: it invites us to think deeply about our place in the cosmos. Are we the product of a finely tuned universe, or simply the lucky winners of a cosmic lottery? And what does this mean for our understanding of reality? These are questions that bridge the gap between science and wonder, reminding us that the universe's mysteries are as much about who we are as they are about how it works. As we wrap up our exploration of these 20 pioneering theories, it's worth stepping back to appreciate the incredible journey we've taken. From the mysterious push of dark energy to the mind-bending possibilities of extra dimensions and quantum entanglement, each theory offers a unique perspective on the universe's accelerating expansion. Together, they remind us that the cosmos is far stranger and more complex than we ever imagined, and that the search for answers is as thrilling as the answers themselves. So, what have we learned? Perhaps the most important takeaway is that the universe's accelerating expansion isn't just a puzzle to solve. It's a window into the deepest mysteries of existence. Whether through the lens of physics, philosophy, or sheer curiosity, these theories challenge us to think bigger, dig deeper, and embrace the wonder of the unknown. And as we continue to explore, one thing is certain: the universe will always have more secrets to reveal. From the mysterious push of dark energy to the mind-bending possibilities of extra dimensions, the 20 theories we've explored today are as diverse as they are profound. Each one offers a unique lens through which to view the universe's accelerating expansion, challenging us to rethink the very fabric of reality. Whether it's the elegant simplicity of Einstein's cosmological constant, the dynamic nature of quintessence, or the radical reimagining of gravity itself, these ideas remind us that the cosmos is far stranger and more complex than we ever imagined. What ties these theories together is not just their ability to explain the universe's behavior, but the profound questions they raise about existence itself. Why does dark energy exist? Is gravity truly constant, or does it change over time? Could the universe be a hologram, a multiverse, or even a cyclical entity that breathes in and out over eons? These aren't just scientific questions, they're philosophical ones, inviting us to ponder our place in the grand tapestry of the cosmos. The beauty of these theories lies in their ability to push the boundaries of what we know. They challenge the foundations of physics, forcing us to confront the limits of our understanding and imagine possibilities that once seemed beyond reach. From the quantum realm to the vastness of space-time, each idea opens new doors, offering glimpses of a reality far richer and more interconnected than we ever dreamed. As we stand on the edge of discovery, it's worth reflecting on how these theories might shape the future of science. Could one of them unlock the secrets of dark energy? Might they lead us to a unified theory that bridges the gap between quantum mechanics and general relativity? Or will they simply inspire even more questions, deepening the mystery of the cosmos? The journey to uncover these answers is as thrilling as the answers themselves, and it's a journey that belongs to all of us. So, as we close this exploration, let's return to the words of Carl Sagan. Somewhere, something incredible is waiting to be known. The universe is full of wonders, and the theories we've discussed today are just the beginning. They remind us that the cosmos is not a static stage, but a living, evolving story, one that we're all a part of. What do you think about these ideas? Which theory resonates with you the most? Let us know in the comments below, and don't forget to subscribe for more deep dives into the mysteries of space. The universe is vast, and the journey to understand it is just getting started. Until next time, keep looking up. The stars have so much more to reveal.